So, idea behind is very simple. High spin, low spin will be dictated by the strength of the ligand. Outer orbital, inner orbital, we have done hybridization. I am talking about the octahedral complex in specific. Electronic configuration, you know how to write it. And the magnetic property, that is high spin and the low spin is related to the magnetic property. Same thing we will take here, students. There are two ways to look at as far as the magnetic property is considered. See, magnetic property, it can be diamagnetic. I am talking about the magnetic property. It can be diamagnetic or it can be paramagnetic. It can be paramagnetic, it can be diamagnetic. In the case of the paramagnetic, we have to know how much paramagnetism it has. How much paramagnetism it has. That is how much paramagnetism it has, or the magnetic moment, what we say, magnetic moment will be spoken by, that is square root of n into n plus 2 Bohr magneton. Sometimes they will ask, find the magnetic moment of the complex. Magnetic moment is equal to square root of n into n plus 2, where n is the number of unpaired electrons. Number of unpaired electrons, right? So this is what speaks about the magnetic moment. What we will do is, students, will take few complexes. For example, we'll take some representative example and we'll try to predict all the properties at once. Okay. So we have done with this. We'll calculate the magnetic moment and the stability. Again, the stability, students, we have spoken about this. I'll just rush through once as far as the stability is considered. We'll just rush through once the stability part. See, stability again will be dictated by, mainly it is dictated by the strength of the ligand. Strength of the ligand will dictate the stability. That is, stronger the ligand, more stable the complex is. More stable the complex is. Stronger the ligand, more stable the complex is. The first thing, first important thing. Second thing is, 4D, 5D greater than 4D greater than 3D. So that is metal ion. This is related to the metal ion. Stability will be higher if there is an involvement of the 4D and the 5D metal ion. I said in the previous session that to make a stable complex, you don't need a strong ligand for the 4D and 5D metal ions. Only you need strong ligand for the 3D metal ions. Additionally, you can take one more point, that is octahedral complexes is more stable compared to that of the tetrahedral complexes. Or in this itself, I will put a point that, students, with this, just to demonstrate, that is, there is a mathematical relation, delta T is equal to 4 by 9 delta naught. 4 by 9 delta naught. Delta T is equal to 4 by 9 delta naught, right? That is, you have around 45%, I would say. Delta T is actually around 45% of delta naught. Delta T is around 45% of delta naught. In this case, they may be giving, for example, delta naught is 10,000. What is the value of delta T? So it is 0.45 of 10,000. So just calculate the value, 0.45 of 10,000. All these small points are important. Remember these things will be asked in the competitive examination, right? So the strength of the ligand is the main factor. Then we'll take, if the ligand strength is same, then we will take care of the metal ion and the complexes. And one more additionally is additional aspect as far as the metal ion. If everything is same, higher the oxidation state, more will be the stability. Stability increases. This point you remember, higher oxidation state the metal ion has, higher will be the stability. For example, if you are having a complex made up of cobalt plus 3 and cobalt plus 2, cobalt plus 3 complex will be more stable compared to that of the cobalt plus 2. Just keep this in mind. So we'll take some of the octahedral complexes, students, and quickly predict all these properties. Then we'll go for the tetrahedral and the square planar complex. There are some of the generalized ideas are there for the tetrahedral and the square planar complex. So for instance, I will take CO, Cl, we have taken already Cl3. So K3, COCl6, K3, FeCN 6 times, FeCN 6 times, right? So vanadium, maybe hexacarbonyl vanadium complex, a positively charged complex it is, that is V plus, right? Then we'll take manganese complex, Mn, water, hexaaqua sulfate complex, we will take it. We'll take copper complex, that is for instance hexa amino copper sulfate complex, we will take it. So these are all the octahedral complex I had taken, and we'll try to predict, students, various behavior of this complex. Can I say this complex is an outer orbital complex? Outer orbital complex? Yes. Can I say the hybridization is sp3d2? Right? It is octahedral geometry. All are having octahedral geometry because there are 6 monodentate ligands. Octahedral geometry it has. Right? Alongside, can I say this is less stable complex? Right? High spin complex. Right, because weak ligand is involved, high spin complex, right? Electronic configuration, we'll try to write the electronic configuration. Electronic configuration, how do you write it? Cobalt, hexamino plus 3 state, cobalt plus 3 students. Remember, you have cobalt plus 3, I'll write it here. You have cobalt plus 3, that is 27 is the atomic number of the cobalt. It's 3D7 4s2, 3 electrons removed, that means it is a 3d6 system. It's a 3d6 system. Very clear, 3d6 octahedral complex. Splitting pattern, if they ask, how do you write it? T2G, Eg, right? T2G is having the lower energy, Eg is having the higher energy. You have 6 electrons. 3 electrons will be filled first in this, then you will be going for the higher energy, that is Eg. 2 electrons you will fill and you will come back and fill the electron here. That means out of 6 electrons, 4 electrons goes to the T2G orbital, 2 electrons will go to the Eg orbital. So if someone asks you how many unpaired electron this complex is having, we'll do one thing, we'll take one by one. We'll just dictate for everything for one complex, then we'll go for the next complex, right? T2G2, Eg2. So this is the electronic configuration of the complex, right? And how many unpaired electrons are there? 4 unpaired electrons are there. 4 unpaired electrons we have for this particular complex. What else you have to predict? You have to predict whether it is a low spin or high spin. High spin you have predicted already, right? Magnetic property needs to be predicted. Magnetic property, how many unpaired electrons you have? 4 unpaired electron. Moment you have unpaired electron, it will be having a paramagnetic behavior. paramagnetic, right? So if you have to calculate the magnetic moment, we'll go through the magnetic moment. Magnetic moment we will calculate. What is the magnetic moment? Square root of n into n plus 2 Bohr magneton. How many unpaired electron we have? 4 unpaired electron we have. Right? 4 unpaired electron means 4 into 4 plus 2. That is turning out to be square root of 24. Am I right? 6 into 4, 24. 24 is near to square root of 5. I mean the square root of 25 is 5. So near to 5. I can write it as 4.8 or 4.9, approximately 4.8 Bohr magneton, 4.86 or something. Right? So that is the one thing. So the second thing is, can we calculate CFSC for this particular complex? CFSC can we calculate straight away? CFSC, how do you calculate? Each electron going to the lower energy orbital will be destabilized. That is 4 into minus 0.4 delta naught plus 4 into minus 0.4 delta naught 2 into plus 0.6 delta naught, right? What is the CFSC for this particular complex? Minus 1.6 plus 0.6 minus 1.6 plus 0.1, sorry, plus 1.2, right? Minus 1.6 plus 1.2, turning out to be minus 0.4 delta naught is our CFSC, or I can write it as 4 dq is the stabilization energy. Minus 4 dq is the stabilization energy for this particular complex, right? What else is left out in this? So that's it, I pretend. That is, I'll repeat again. So it's an octahedral complex, sp3d2 hybridization, octahedral complex, outer orbital complex, less stable, high spin complex, T2G4 Eg2 is the electronic configuration, 4 unpaired electron it is having, magnetic properties paramagnetic, magnetic moment we have written, CFSC also we have calculated. This is the story behind this particular complex. Very, very important, students, to understand everything about the particular complex.